In the next lecture, we will look at how to derive these equations of motion using computer tools. Okay, so this is a little bit of descriptive. If you want to learn how to use computer tools, then we have to sit in front of a computer. Just listening to these slides or these lectures are not enough. But nevertheless, we will go through step by step as to how to start or use these computer tools so that we can finally derive the equations of motion. The equations of motion for a multibody mechanical systems can be very complex. Okay, we have seen very simple systems of 2R and maybe a disk which is rolling, but any mechanical system which is reasonably big can have many parts, and hence the equations of motion can be very complex. Even in the examples which I have showed you, there are many terms, and the extensive use of trigonometry, algebra, matrix operation, and calculus. Okay, we have done derivatives, partial and time derivatives. Even for the simplest possible multibody serial chain, the planar 2R, if you go back and see the mass matrix, the 1 term, so the first term in the mass matrix has 6 terms with algebraic and trigonometric operations. So think of it, if you have a robot with 6 degrees of freedom with many parts, you will have many more terms, okay, and each of these terms will have many algebraic and trigonometric operations. So you'll have sine and cosine of angles and so on. So it is imperative that we find some computer tools which can give you these error-free expressions and equations of motion. It is physically impossible, almost impossible, to derive by hand or manually the equations of motion of any reasonable mechanical system. There are two kinds of computer tools which are available. One is what is called as a computer algebra system, or CAS. These systems perform algebra, differentiation, simplification, etc. on the symbolic expressions. Okay, so we will not give numbers, we will give symbolic expressions as some kind of a text, and then these computer algebra systems can do addition, multiplication, then differentiation of the symbolic expressions. So if you do all these symbolic expressions, for example, in the Lagrange formulation where we do partial derivatives with respect to qi and qi dot and so on, we can arrive at the equations of motion by doing all those expressions symbolically. There is also another kind of computer tools which are for modeling and simulation of mechanical systems and other systems also. So most of these tools come integrated with a CAD tool, and basically they will do numerical solutions of the equations of motion. So we will see some of these expressions or tools later on. So let's continue. So an example of a computer algebra system is Maple. Okay, so we have used Maple extensively in this course and for various applications to obtain equations of motion and even for rotation matrices. So I thought we can just go over very quickly how does Maple work. Okay, what are some of the important elements of Maple? We can also have examples of modeling and simulation tools for multi-body systems. Two of the well-known ones are Adams and Simscape. So we will start with a brief introduction to Maple with examples. So this requires a lot of practice with Maple. So the purpose of this talk or this lecture is to tell you how to go about starting Maple and do some very basic simple operations. Once you start doing this, then you can see it's a very powerful tool which can be used for many applications. In the next module, next week, we will look at a brief introduction to Adams and Simscape. The Adams and Simscape are basically modeling and simulation tools where we can model a multi-body mechanical system and then we can ask it to simulate. Basically, we can solve equations of motion for given initial conditions and for given parameters of the mechanical system and find how the mechanical system moves. So let's continue. We have Maple. Maple is a symbolic manipulation package available from MapleSoft. So this is a company and you can go to this website www.maplesoft.com for more details about Maple. It is available in academic and student versions. The current version of Maple is 2022, Maple 2022, and it's available in Windows and Linux. Many products and modules are given by this Maple company, MapleSoft. We are only going to look at a small subset which are useful for obtaining expressions related to kinematics and dynamics of rigid multibody systems. There are many other modules. Please go to the website here and you can see what all features and what all packages and what all specialized packages are available from this company. In its most basic form, Maple can perform various mathematical operations, okay, which are represented as symbols and strings. It can simplify expressions using mathematical identities and results to obtain expression in simplest form. So for example, if you have some sine squared theta plus cos squared theta appearing somewhere in your derivation of equation of motion, it can convert that using trigonometric identities to 1. The output of Maples are also symbols and strings. Okay, they are not numbers. They can be numbers, but you can use Maple to obtain expressions of equations of motion, and I will show you examples. The output can also be evaluated numerically by assigning numbers to the strings and symbols. So if you have an output which says cos of theta, okay, and if you give the value of theta as some angle, it will evaluate cos theta and give you a number. The output can also be integrated with text and math, graphics and images, and other forms of presenting information. Okay, it can give you plots of some variable as a function of time and so on. In this NPTEL course, as I have mentioned, Maple has been used extensively to obtain error-free expressions of linear and angular velocities of rigid bodies and multibody systems. The error-free equations of motion for examples of serial and parallel chains. So for example, the planar 2R or even the 4-bar mechanism. The Maple outputs have been integrated with MATLAB to obtain plots and numerical solutions. There are 3 examples which I am going to show you of using Maple in this lecture. First is we obtain the angular velocity of a rigid body B in a reference coordinate system A for Z, Y, X Euler angles. Okay, so I will show you how we can obtain the rotation matrix, then we can obtain R dot R transpose, and then from this Q symmetric matrix we can extract the components of the angular velocity vector. I will also show you how to obtain the equations of motion for a planar 2R serial chain. In fact, in the examples which I have shown earlier, the equations of motion were obtained using Maple. And likewise, I will show you how to obtain the equations of motion for a 4-bar mechanism. So this is a parallel chain, this is a serial chain, and this is some simple kinematics requirement to obtain angular velocity of a rigid body. Just continue a little bit of introduction of Maple more. Maple is a symbolic and numeric computing environment. as well as a multi-paradigm programming language. Please go to the Maple website and you can understand what are some of the really powerful features of Maple. It covers several areas of technical computing, symbolic mathematics, numerical analysis, data processing, visualization, and others. Maple rose from a meeting in late 1980 at the University of Waterloo in Canada. The first version was available in January 1982, so it's a fairly old and mature software. Maple incorporates a dynamically typed imperative style programming language. Okay, we'll see what it means. So basically you'll have a command prompt, and then if you type and you can ask it to find out what it means or what it evaluates. Maple also has interfaces to other languages, C, C#, Fortran, Java, MATLAB, and various other languages. And it can also integrate with Microsoft Excel. So here is a starting screen of Maple. So once you download Maple, and then if you initiate Maple, so then you can get this something like this screen. Okay, so this screen has various features. First is this menu bar. So like any other Windows operating system, you have file, edit, view, insert, format, and various other things. Okay, below that you have this Maple toolbar. Okay, it tells you, we will go into a little bit more detail, it tells you what are all the things it can do. Okay, then there is on this left side there is a palette, which is basically it gives you all the most common mathematical operators, symbols, and their expression. Okay, and we can easily use this toolbar to do in this workspace what to do or how to initiate conversation with Maple. So for example, you can also do it, click some start button to start a new file. There are many others, help files, which are also available. So the start screen of a new workspace looks like this. Okay, so you have some favorite expressions, calculus, and so on. And when you start it, you will get a prompt which looks like this. Okay, so in Maple, the program is run line after another. So if you type something here, then when you enter, it will execute the line, and the output is shown in a blue line just below it. And I will show you examples. You can give multiple commands and executions can be performed in a single line. So for example, if you can end one command with this colon or this, and you can keep on typing all the commands one after another. So a colon at the end of the command suppresses the output. So even though you do enter, there will be no output which is shown. Okay, and a semicolon or keeping it blank for a single command shows the output. To assign any variable, we have to say a colon equal to something. Okay, we cannot use equal alone. Okay, and if you change anything in the previous line, every line after it needs to be executed because it doesn't know what you have changed in the previous line. So some useful comments about Maple. It's a good practice to include common libraries like linear algebra or student linear algebra, which covers most of the commonly used functions. Okay, the syntax is you initiate this line with quote with package name, so with linear algebra. Most common calculus, trigonometric, Greek, linear algebra, vectors and matrices, symbols, etc. are available on the palette on the left. So remember I showed you our palette. These are for common trigonometric and calculus and linear algebra operations. You can use combine and simplify to make the output compact. So as I gave you an example, if you have sine squared theta plus cos squared theta, you can say simplify and it will give you back 1. It will use some inherent trigonometric identities which are pre-programmed to simplify these expressions. Sometimes using subscript and superscript causes issue while differentiating. Okay, so if you want to differentiate cos theta, Okay, Maple, if you say differentiate cos theta, it will give you minus sine theta. So it is, you need to practice once in a little bit to find out exactly what this is happening. So sometimes you need to substitute the variables with which you want to differentiate. So for example, syntax is substitute, x of t is a, y of t is b. Okay, so you cannot differentiate maybe x bracket t, but you can differentiate a, and there are some expressions like that. To multiply matrices and vectors, we have to use a dot like this, and again these examples we'll see. For transpose, okay, we can use this caret with a plus sign, okay, not like t, which is what I have shown in the text. Or you can say transpose a variable name. So if you have a x and you want to do x transpose dot y, then we have to use this quote plus, this caret and plus. The matrices can be differentiated by quite simply, okay, all you say is use map diff matrix name comma t. T is the variable with which you are differentiating each element of the matrix. Okay, so t is like time. It could be some other theta. You have to tell this element of the matrix need to be differentiated with this variable t. To get the coefficients of any variable in an expression, use collect. So if you have a long expression and if you want to find out what is the coefficient of theta 1 double dot, remember in the equations of motion, I had theta 1 double dot, and inside a bracket, I had I1 plus I2 plus M1 R1 square and so on. So how did I find all the coefficients of theta 1 double dot? You can use a command like this. And we can use very simply rotation matrix in the angle axis form. So these are some specialized commands which are useful for this course, because we can use these commands to do some kinematics and find rotation matrices and so on. So let's continue. We want to use Maple. So what is in the palette? So I hope you can see it here. We have some a plus b, a minus b, a by b. So all these various operations are already there. We can also find the derivatives, and you can find limits, and then you can also integrate. So Maple allows you, or it will evaluate certain integrals which it knows. And then you have these common symbols, and then you have variables, matrices, units, and so on. So most easy to write variables and expressions just by clicking on this. So you click on these symbols and it will appear on the worksheet. You can also edit it if you want to. Variable name cannot have spaces in it. This is something which, once you start using it, you will find. So it should be continuous. So you cannot have a blank b. It will not like it. You have to write ab. Both prescripts and postscripts, superscript and subscripts, can be used in variable names. Okay, so you can write x1 and subscript and so on. So you can see here that there is a to the power b. Okay, and so you can write variables name like a to the power b. The values assigned to variables can be viewed in the variables tab. So there is a variable tab here, and if you say that x is some 2 or 3 or some number, okay, then that can be seen here. So let's use Maple to obtain the angular velocities for z, y, x Euler angles. Okay, so this is one of the examples which I thought if you go through it, then you can see what exactly we need to do. So the first thing is, in this prompt we say with linear algebra, with student linear algebra. This is including the packages linear algebra and student linear algebra. One thing what you can see is I have written something R1 colon equal to rotation matrix theta 1 0 0 1. So what it means is that I want to rotate about a vector 0, 0, 1, which is nothing but the z-axis, by an angle theta 1. So if you type this in that command prompt in Maple, then you will get this matrix. So you can see R1 is cos theta 1t minus sine theta 1t, 0, 0, 1, sine theta, cos theta, and so on. This is a simple rotation about the z-axis. And it is very, very simply, you can do it in one step, and it comes out, as I said, written in blue. So this is the output of Maple when you type this command. And we need to, you can see that this is nothing but a rotation about the z-axis by an angle theta 1. Then we can do similarly R2, which is the rotation about y-axis by an angle theta 2. Okay, so you will get R2 like this. And remember, we are going to later on differentiate. So we want to ensure that theta 1, theta 2, and likewise theta 3 are functions of time. So R3 is this. So rotation matrix theta 3, 1, 0, 0. This is the x-axis. So I want to find out what is the resultant rotation matrix after z, y, x. So we multiply it in the order which we have done these rotations. So first z, then y, then x. You multiply, and then you will get this little bit long expressions. But if you just carefully see, what it is telling you is, for example, this element, which is the 3, 1 element, is minus sine theta 2t. Okay, this one is cos theta 2, cos theta 3t. Okay, this one is cos theta 1t, cos theta 2t, minus sine theta 1t into cos theta 3t, plus so on. So this is the first column vector, which is the xb in the a coordinate system. This is the yb in the a coordinate system, and this is the zb in the a coordinate system. And you can go back to your notes and see that this is exactly what we had written in the text, okay, when we were looking at Euler angles. So as you can see, with these three steps and one more which is here, I can find the rotation matrix corresponding to z, y, x Euler rotations. Then let's find out take steps to find out the angular velocity. So I want to do actually r dot r transpose, because I want to find the space fixed angular velocity vector corresponding to z, y, x Euler rotations. So what you can see is we need to type omega s, which is the skew symmetric matrix, is simplify map diff rt then r transpose. So when you say diff rt, it is trying to do r dot. Okay, and then when you say this dot r transpose, so remember transpose corresponds to a plus. Okay, so when you type r transpose, r plus, it will go back and see what was r earlier, and then it will do transpose of that matrix, and then this is r dot. And this simplify is to write it in a compact form. So wherever possible, it will try to simplify using trigonometric identities, and any other, if something is 0, it will make it 0. Okay, so remember, in a skew symmetric matrix, the diagonal terms should be 0, and it will automatically make it 0. So how does it know this is skew symmetric matrix? It will basically, after doing simplification, it will see that these elements are 0. And hence, we can find what is this skew symmetric matrix. So you can see that the diagonal terms are 0. The off diagonal terms are aij is minus aji. So for example, this term is sine theta 2, and this is theta 3 dot. This is the way theta 3 dot is represented. So this is minus d by dt of theta 1 as a function of time. So this quantity is theta 1 dot. Okay, this is minus sine theta 2 theta 3 dot plus theta 1 dot, and these two terms as aij is same as minus aji. Likewise, we can find all other terms. So as you can see, we obtain clearly little bit different than how you write with hand, but all the terms are there. So this is theta 3 dot, theta 1 dot, minus sine theta 2. If you look at, let's say, another example, this point, this is minus cos theta 2, this is theta 3 dot into cos theta 1, plus this is theta 2 dot into sine theta 1. Okay, so this matrix comes out when you do this steps in Maple. Then we can see that this is a skew symmetric matrix. This is minus and this is plus. This is minus and this is plus, and so on. It has all the rules of a skew symmetric matrix. So we can extract from this skew symmetric matrix the space fixed angular velocity vector, which is the x component is omega 3 2, which is this one here, then 1 3, and then 2 1. Okay, so this is the z component. So we can obtain all these components, and then as soon as you type this, it will come out and show you that these are the components of the angular velocity vector. Okay, so in our notes we have called this omega r. So this is right multiplication. We started with r into r transpose is identity, then we took the derivatives and so on. So here in this slide it is being called as omega s. And you can see omega x is, so cos theta 2 into theta 3 dot into cos theta 1, and then minus theta 2 dot into sine theta 1. So you can go back and verify, because these expressions are given earlier in the text, that this is indeed the x component of the angular velocity vector. And then if you want to see whether it can be written in a more compact form, you can say simplify r transpose, okay, r dot, which is the body fixed angular velocity vector also we want to find out. And then again we can find this. These are the components of r transpose r dot. And the body fixed angular velocity vector is again the 3 2, 1 3, and 2 1 components of this skew symmetric matrix. Okay, so again you can see that you can get the angular velocity vector components either in the space fixed, which is omega s, or in the body fixed, which is in this form. So the summary of this is we can start with a rotation matrix, which is nothing but rotations about z, y, and x. Then we do this differentiation of this rotation matrix, and then we type these commands, and we get the angular velocity in the of the body in either space fixed or body fixed angular velocities. Let's continue. We want to show you how to obtain the equations of motion of a planar 2R manipulator. So this will take a little bit more time, but nevertheless it's a good way to see the power of Maple and how we can get error-free equations of motion. So again we start with some packages, which is linear algebra and student linear algebra. First thing is we say what is the location of the CG of each link. Okay, so 0 PC1 is the position vector of the first link center of mass or center of gravity. And if you can see in your notes that this is nothing but r cos theta 1 and r sin theta 1. We have to say explicitly that theta 1 is a function of time, because later on we will take the derivatives. So as soon as you type this, and since you are not suppressing the output, you will get this vector that 0 PC1 is given by r1 cos theta 1t, r1 sin theta 1t, and the z component is 0. Likewise, the location of the CG of the second link, which is after the first link, is L1 C1 plus R2 C12, L1 S1 plus R2 S12. So again, you can see it is L1 cos theta 1t, r2 cos theta 1 plus theta 2t, and so on. And as soon as you type this, you will get the position vector. So these are consistent with what is mentioned in the notes, and this is very easy. So you have to give these inputs. So you need to know that this r1 cos theta 1t is the x component and r1 sin theta 1t is the y component. But that is very simple. Okay, we are not not doing very tricky things. That from the figure you can see what is the position vector of the center of mass of each link. Then we can find the velocity of the center of mass, and as I said, we differentiate 0 pci, which is the position vector, with respect to time. Okay, and this map, this means that you want to differentiate this position vector, and when you differentiate, you can see the output is r minus r1 d by dt of theta 1t. So this is like theta 1 dot into sine theta 1. Okay, so x coordinate was cos theta 1, r1 cos theta 1, y coordinate was r1 sine theta 1. So it does this differentiation of symbolically, and it will give you r1 theta 1 dot sine theta 1 written in this form. Okay, similarly the y component was the derivative of r1 sine theta 1, so you will get r1 theta 1 dot cos theta 1. And likewise we can find the velocity of the CG of second link, again by taking the derivative of 0 pc2 with respect to time. Okay, this tells you that you are taking the derivatives with respect to time, and again you will get various terms. So remember, it was L1 C1 plus R2 C12. That was the x coordinate of the center of mass of the second link. So when you take the derivative, it will be minus L1 theta 1 dot sine theta 1, then minus R2 theta 1 dot plus theta 2 dot. You can see even these brackets come up nicely. So you know exactly this is what is theta 1 dot and theta 2 dot. And then we have sine theta 1 bracket theta 2, theta 1 plus theta 2. The y component is similarly derivative of sine. So you will get cos and then theta 1 dot and so on. So you can find the velocity of the CG of the first link and the second link using Maple. Again, these are error free. Okay, the way it is written, this computer tool it's not going to make mistakes. So it will not going to put some different sign here by mistake. The kinetic energy now can be obtained because we know the linear velocity of the center of mass of each link. So what is the kinetic energy? It is nothing but m1 into vc1 transpose vc1. So this transpose means basically it is like vc1 dot with vc1. Okay, so dot is like v transpose v. So if you have a vector A dot vector B, I can write it as A transpose B. So that is what is exactly being done here. So this is half m1 vc1 square. This is half m2 vc2 square, and then you have I theta 1 dot square, then I2 theta 1 dot plus theta 2 dot square. So this is I1, which is the moment of inertia of the first link, and we are only interested in the z component. Okay, that we need to make sure that we are doing a planar example, so only the z component will appear. So you type this and the Maple will give you this output. Okay, so this output is a little bit different than how you write it by hand, but basically you see that this whole thing is divided by 2. So you have basically something like I1 plus I2 and then theta 1 dot square half. So this half is coming here like this, and then you have this theta 2 dot into some term which is dependent on cos theta 2. Remember, in the kinetic energy there was one term which was function of theta 2 and the rest were constant. So that is what this term will come. Okay, we can also find out the other terms. So this is the for the second link. This is theta 2 dot square into m2 r2 square plus I2, and then this half will appear because it is like half mv square, right? So r2 into theta 2 dot is like v and half mv square. So this half will come here. Okay, this is the output of Maple. So it looks a little different than how you would write by hand or do it manually, but nevertheless this is correct if you just see a little carefully. The potential energy can also be obtained by m1 into g dot this position vector. Remember, that is the way we defined the position vector. It's like mgh. So instead of h, we have a dot product with g vector, which is along the y direction, into this. So we will get m1 g r sine theta and m2 g l1 sine theta 1 plus r2 sine theta 1 plus theta 2, because the second cg is after the first end of the first link, which is L1 C1 and L2 S1, L1 S1 and L1 C1, and then you have this R2. You go along the second link by a distance R2. So we can find the potential energy, and then we find the Lagrangian, which is Ke minus Pe, and again as soon as you type this, it will give you this long expression. So is this correct? Yes, because you need to go through a little bit carefully and see that this taken the kinetic energy here, which is this long term, and then it has taken this potential energy and it is subtracted, so it looks okay. Okay, so we can find the Lagrangian, and importantly it is in a symbolic form. Okay, so we should be able to take the partial derivatives and time derivatives of various terms whenever required, because it knows that theta 2 is a function of time. I1, R2, M2, these are not functions of time, they are constants. So we define a substitution for the variables, making it easy to differentiate with respect to the variables, because we say that we want to differentiate with respect to theta 1, theta 2, and also with theta 1 dot and theta 2 dot. So we define these new variables d theta 1, d theta 2, and theta 1 and theta 2. Then we can say that these are like, you can switch the order and say that d theta 1 by dt is basically this new variable d theta 1. Okay, and d theta 2 is this variable d by dt of d theta 2. Okay, and we obtain partial of Lagrangian with respect to d theta I dot. Okay, we are substituting to get the variables independent of time. So when you do partial derivatives, you are taking derivative with respect to theta dot. Theta dot itself is a function of time. So we don't want to confuse Maple into thinking that you should do it like a chain rule, first with respect to theta and then again d theta by dt and things like that. So we will take this partial derivatives with respect to the theta I dot, okay, and then later on, if when required, we will differentiate with time, okay, and then we will convert it back to actual functions of time. So what do? We assign two variables, temp1 and temp2. So temp1 is this long expression. Remember, this was part of the kinetic energy. Temp2 is this also reasonably long expression. And then we will take this partial and time derivatives. So the first equation is implementation of d by dt of dl by d theta I dot minus dl by d theta I. So this is the partial of the Lagrangian with theta I. This is the partial of the Lagrangian with theta I dot, and then the time derivative of this. So what you can see is we are taking this r time, which was defined earlier, and L, and we are going to differentiate with respect to theta 1 here, because this is the first equation. Similarly, here we are going to differentiate temp 1, which was there, with time. Okay, and then if you do this, simplify this whole expression, you will get terms like this. So the first equation is cos theta 1, cos of theta 1 plus theta 2 into m2 r2g. So this is like m2 r2g c12. Then this is like 2 c2 m2 l1 r2. So this is also a term in the equations of motion if you go back and see. Then you will have m2 into I1 square, L1 square plus R2 square, and this is M1 R1 square, and this is I1 plus I2. Whole, everything is multiplied by second derivative of theta 1. Okay, likewise we will get terms which are other terms. So for example, you will get something like L1 M2 plus M1 R1 into G cos theta. So once you start using it, you will see that this is parts of the equation, but not in the most simplified form. Similarly, the equation 2, we take the derivative with respect to theta 2 partial, then we take the derivative of this with respect to time, okay, and then we again simplify. So the equation 2 contains m2 L1 R2 cos theta 2 plus I2 plus m2 r2 square into theta 1 double dot, and that is correct. Okay, this one is very easy to see. The m22 element, the second element in the second equation, okay, so m22, that is m2 r2 square plus I2 into theta 2 double dot. So these equations you can obtain using Maple by simply basically taking the derivatives, required derivatives, partial with theta I, partial with theta I dot, and d by dt of this part. And then of course you have to simplify. So you need to get used to it, try it a few times, and then you will see that it does make sense. Okay, it is not the way we write it by hand, because we would write it like M2 L1 R2 C2, but here Maple is giving the output, the string or the text output is in some sense in the opposite way. Okay, so M2 R2 square plus I2, this is more or less okay. Okay, this is maybe the way you would write it by hand also. Maybe you would write it as I2 plus M2 R2 square, because this is the use of the parallel axis theorem. From CG you are going to some other point. Next, once we have these two equations, okay, we want to write it in the standard form, which is M mass matrix into theta double dot plus Coriolis centripetal term plus gravity term, and then we will say this is equal to tau 1 and tau 2. So how do I find the element of the mass matrix? So what you can see is if you type coefficient 1 of equation 1, which is this long expression, and then you see what are the coefficients of d2r by dt squared theta 1t. So basically what is the coefficients of theta double dot in equation 1? Okay, so if you type this, it will search and collect all the coefficients which are multiplying theta 1 double dot. Similarly, this is the coefficient of theta 2 double dot in equation 1. This is equation 1. And the mass matrix element, this one, is the coefficient of theta 1 double dot in equation 2, which is this. And this is M22 element, which is the coefficient of theta 2 double dot in equation 2. Straightforward, right? So then you type this, and then Maple will give you this, and here you can see that it is looks okay. So the first element M11 is this long term, which is I1 plus I2 plus M1 R1 square plus M2 R2 square plus M2 L1 square. So Maple automatically will combine these two, and then you have 2 cos theta 2 M2 L1 R2. The 1 2 element is I2 plus M2 R2 square plus M2 L1 R2 cos theta 2, and you can see this is a symmetric matrix. So 1 2 is same as 2 1, and the 2 2 element is this. So if you go back and see the notes, or if you go back and see the lectures where we derive the equations of motion, that this is indeed exactly the terms which you will get, written slightly differently, but nevertheless these are exactly the terms that you will get for the mass matrix. How do we obtain the Coriolis term and the gravity term? We will use this nice interesting formula for the Coriolis term. This was shown in the lecture, that you take the ij element of the mass matrix, partial derivative with theta k, then ik element, partial derivative with theta j, minus kj element, partial derivative with theta I, then you multiply the whole thing with theta k dot, and then you sum over k equals 1 to 2. In this case there are only two of them. So ij will be the variables which are not summed over, okay, so indices which are not summed over, and you will get C11, C12 and so on. So this is the matrix corresponding to the Coriolis and centripetal term. How about gravity? We know what is the potential energy. We derived what is the expression for the potential energy. So the first ith term in the gravity will partial derivative of PE with respect to theta I. And once you do all these things, and then you type this command, which is m. So we are going to do some temporary things, which is theta 1 is q1, theta 2 is q2, and this is the mass matrix. Because we want to take the derivatives of the elements of the mass matrix, we type a few terms like this, and you can find that the coefficients of, or the elements of the Coriolis Cij will come out. So C11 is this, C12 is this, C21 is this, and C22 is 0. Okay, and the gravity terms are nothing but the derivatives of the potential energy and with respect to theta 1 and theta 2, and again we will get these terms. So you can see yourself, open the notes, open the other notes, and then you can see that these are indeed the terms corresponding to the gravity, and these are indeed the term corresponding to the Coriolis and centripetal term. So let's continue. I also want to show you how we can obtain the equations of motion of a planar 4-bar mechanism. So again, basically we start with some packages, linear algebra and student linear algebra. Then we write down the position of the center of mass of each one of these links. So 1, 2 and 3. And again you can see that the third link is you go along the x-axis by L0, and this is R3 cos phi 1 and R3 sin phi 1. So these are the position vectors for the 3 position of the CGs of 3 of these links. The velocity of the center of mass or the center of gravity can be obtained by taking the derivatives of this position vectors with time, and again you will get minus r1 theta 1 dot sine theta 1 and so on. Similarly, the velocity of the second link, CG of the second link, can be obtained by taking the derivative of PC2, okay, with respect with time, and again we will get all these terms. So we will have theta 1 dot, but you will also get phi 2 dot, because remember the position vector of the end of the CG of the second link has theta 1 and phi 2, whereas the position vector of the last link, the output link, contains only phi 1, and when you take the derivative you will have minus r3 into phi 1 dot into sine phi 1 and r3 into phi 1 dot into cos phi 1. Once we have the linear velocity of the center of mass of link 1, link 2 and link 3, we can find the kinetic energy of link 1, which is half m1 v c1 square, plus half m2v c2 square plus half m3v c3 square plus the contribution due to the inertia about the z-axis, which is I1 theta 1 dot square plus I2 theta 2 dot square theta 1 plus theta 2 dot square plus I3 phi 1 dot square. So once you type this in Maple, you will get the expression for the kinetic energy, which looks like this. The potential energy of each of this link can also be obtained by taking the dot product of the gravity vector with the position of the CG, the vector. And remember, this one is plus means here transpose and dot means multiplying these two vectors. So likewise, this is M2GH plus M3 into GH, roughly speaking. Of course, we will have sine and cosine of the angles theta 1 and then phi 3 and phi 1, and also we have sine of theta 1 and then we have R2 sine of theta 1 plus phi 2 and so on. The sine component is the height from the zero potential energy surface. Once we have the kinetic and the potential energy, we can obtain the Lagrangian, which is now a function of theta 1, phi 2 and phi 1, and also the derivatives of this. So the kinetic energy contains the derivatives of theta 1, phi 2 and phi 1. And the potential energy is a function of only theta 1, phi 2 and phi 1. Similar to this case when we did for the 2r, we define intermediate variables s time and r time, which are basically theta 1 to say that theta 1 is a function of time, phi 1 is a function of time, d theta 1 is basically theta 1 dot, but it is assigned a new variable d theta 1, because when we take the partial derivative of this Lagrangian with respect to theta 1 dot, this is the easy way to do it, or this is the simplest way to do it. And likewise, we have another variable r time, which is again as used in the case of the planar 2r. We find it is useful to introduce these two variables. Then once we obtain the Lagrangian, we can take the derivatives with respect to qi dot. Note again, we are substituting to get the variables independent of time. We want to differentiate Lagrangian with respect to qi dot. Qi dot itself is a function of time, inherently a function of time, but we don't want to differentiate with respect to time. We want to do partial derivative of Lagrangian with respect to qi dot. Okay, then later on we can always go back and substitute and find it as an explicit function of time. So we have these two variables, temp1 and temp2. Temp1 is basically the Lagrangian with respect to d theta 1 or theta q1 dot, and temp2 is the Lagrangian with respect to d phi 2, which is phi 2 dot. Okay, so hence if you do these substitution, these derivatives, then you can show that temp1 will give these terms. Okay, these are some parts of the equation of motion. This is only the derivative with respect to qi dot, partial derivatives with respect to qi dot. This is the partial derivative with respect to phi 2 dot, and then similarly this is the partial derivative with respect to phi 1 dot. So we will get these three terms, and we have assigned these temp1, temp2, temp3 because later on we have to take the time derivative of each of these terms. Remember, Lagrangian is time derivative of the partial of d Lagrangian with respect to qi dot minus d Lagrangian with respect to qi. So we obtain the time derivative of dl by dqi dot minus dl by dqi. Okay, and hence we get three equations. One is equation 1, then we have equation 2, and then we have equation 3. So these are the terms of the left hand side of the equations of motion. So as you can see, we have some m3 r3 square plus I3 into phi 1 double dot. And then we have this gravity term, which is m3 g r3 cos phi 1. So this is for the output link. The output link has no connection with theta 1 and phi 2 yet. Okay, we will connect theta 1, phi 2 and phi 1 using the constraint equations. So we now have equation 1, which contains all the terms which we are interested in, which is theta 1 double dot, phi 2 double dot, and also the Coriolis and centripetal terms. So you can see here there is a phi 2 dot square. Okay. And likewise for equation 2, we have, which is theta 1 double dot plus phi 2 double dot, plus we have this Coriolis term, which is theta 1 dot square, and of course the gravity terms. Once we have these three equations, equation 1, equation 2, equation 3, so this is nothing but the left hand side. So we will later on equate it to the external torques, but before we do that, we can collect the terms in the mass matrix. In this case, the mass matrix is 3 by 3 because we have three variables. We have theta 1, phi 2 and phi 1. And just like before, we collect the coefficients of equation 1, which are, theta 1 double dot into what is multiplying the theta 1 double dot. And likewise, we find the coefficient of theta phi 2 double dot from equation 1 and coefficient of phi 1 double dot from equation 1. So this will be the first row of the mass matrix. The second row will be given by this, and the third row will contain the coefficient of theta 1 double dot in equation 3, phi 2 double dot in equation 3, and phi 1 double dot in equation 3. So once we do these steps, we can see what the mass matrix looks like. It is very similar to the planar 2R. So the top 2 by 2, okay, so M11, M12, M21, M22 are exactly the same as the terms in the mass matrix in the planar 2R. Because why? Because we have broken the 4-bar mechanism into a 2R mechanism, planar 2R chain, and a single 1R chain. So the 2R part looks exactly like this, except we don't have theta 2. In the planar 2R, we had theta 1 and theta 2. Now we have theta 1 and phi 2. In the planar 2R, the mass matrix was a function of theta 2. We had cos theta 2, and so on. So here we have cos phi 2 and 2 cos phi 2. The interesting part is here. The third column is 0, 0, m3 r3 square, and the third row is 0, 0. Okay, with this 3, 3 element being m3 r3 square plus I3. So what you can see is this third column and the third row, except this term, everything is 0, and there is no relationship with theta 1 and phi 2. Okay, this will multiply phi 1 double dot plus whatever is the centripetal and Coriolis term. Okay, there is actually no Coriolis term, plus gravity term for the third equation. So in the third equation, you can see m3 r3 square plus I3 into phi 1 double dot plus m3 g r3 cos phi 1. So this is nothing but a pendulum with R1R link, a single link which is being rotated at the angle with angle phi 1. So the mass matrix does not have any relationship between the top 2 by 2 and the last 3 by 3, 3,3 element. This will come once we obtain the constraint equations. But before we go to constraint equation, let me again show you how we can compute the Coriolis and centripetal term and the gravity term. So the gravity term is again the partial derivatives of the potential energy with respect to Qy. Here Qy is theta 1, phi 2 and phi 1. And similarly, we have all these partial derivatives of the elements of the mass matrix with respect to Qk, Qj, Qi multiplied by Qk dot, sum over k equals 1 through 3, because now there are 3 of these elements. Okay, Q's are 3-dimensional. So once we have this, we can obtain what are the elements of the Coriolis and centripetal matrix or terms, which is given by C, and that we obtain by substituting Q1t as theta 1, Q2t as phi 2, Q3t as phi 1, and then we look at this temp, which is some way to capture what is the derivatives of these mass matrices. Okay, so once we do all that, we can see that the Coriolis matrix, there is one C11 term, C12 term, C13 is 0. So this part is 0 because you can see this 0 because the Coriolis term for the output link M33 is constant. Okay, so M33 is constant, so derivative of M33 with everything will go to 0. The gravity term likewise is a partial derivative of the potential energy with respect to Qi. Again, you will get some mg cos theta, and then for the third or the output link, we will have m3 gr3 cos phi 1. Okay, so this will be theta 1, then you will have some theta 1 plus phi 2, and the y component will be m2 r2g cos of theta 1 plus phi 2. So we can find the mass matrix, we can find the Coriolis matrix, Cij, and we can find the gravity terms. So this is a vector, this is a 3×1 vector, Coriolis is a 3×3 matrix, and mass matrix is of course 3×3. Now let us look at the constraint equations. So what do we have? We have two constraint equations. Remember, for a 4-bar mechanism, when we break at the joint 3, so we can find the position vector of the joint 3, which is L1 cos theta 1 plus L2 cos theta 1 plus phi 2, and this will be equal to the vector going from the other direction, which is L0 plus L3 cos phi 1t. So one of the constraint equation is L1 cos theta 1 plus L2 cos theta 1 plus phi 2t minus L0 minus L3 cos phi 1t equal to 0. Okay, this is what is given here. So we define one constraint. Then the second constraint is the y component, which is L1 sin theta 1 plus L2 sin theta 1 plus phi 2. This will be equal to L3 sin phi 1t, and so you can take this on the one side, and this is equal to 0. So constraint 1 is equal to 0, constraint 2 is equal to 0. These are the two constraint equations. In the earlier part of this week, I had said eta I of q. So this is eta 1 of q and this is eta 2 of q. So there are only two constraint equations. So then we can differentiate this constraint equation and find the constraint matrix. So the constraint matrix is given by psi. And how do I find out? We find the derivative of this constraint equation 1 with time, the derivative of the constraint equation 1 with 2 with time, and then we say that these are d constr1, d constr2, and we get some terms. This will contain theta 1 dot, then it will contain phi 2 dot, and so on. Because we are taking the derivative of this constraint equation, so we will have to use chain rule. So L1 cos theta 1 will become minus L1 sin theta 1, and then also one more term with theta 1 dot. So this is what you will get. Okay, so we find the derivative of this constraint equation and label them as d constraint 1 and d constraint 2. So the coefficients of the psi matrix, the constraint matrix, can be obtained by finding the coefficients of theta 1 dot from d constraint 1. Similarly, the coefficient of theta 1 dot in d constraint 2. the second derivative of the constraint equation, and likewise the coefficient of phi 2 dot from the first equation, phi 2 dot from the second equation, and then phi 1 dot from the first equation and phi 1 dot from the second equation. So we will get a psi matrix as 2 by 3. So there are 2 rows and 3 columns, and these are the terms. So this is one term, this is the second term, and this is the third term. So we get the psi matrix, which is a 2 by 3 matrix. We also need to find the derivative of the psi matrix, which is denoted by dp psi. And how do I find the derivative of the matrix? We use this command map diff psi of t. So basically we take the derivative of each element of this matrix with time, and then we labeled it as dp psi. So here again we will get the derivatives of each one of these terms, and these are given here. So we can take a look at one of the terms. Let's say L3 sine phi 1 t. So what will be the derivative of this? It will be L3 into phi 1 dot into cos phi 1 t. Just simple chain rule. So the derivative of minus L3 cos phi 1 t is L3 phi 1 dot into sine of phi 1 t. Okay, so we can find each of these elements, the derivatives, and arrange them. So the dimension of psi dot is also 2 by 3. So once we have found out all these things, we can use the elements of the Jacobian of the constraint matrix. We can find the equations of motion, and then we can derive the equations of motion. One thing which we can do is we can convert whatever we have obtained to MATLAB, because eventually we have to solve these equations of motion in MATLAB. Maple also allows you to solve equations of motion, but MATLAB is more better known. It has better GUI, and you can get plots and other things very easily. So we can convert whatever Maple is producing, all the symbols and expressions, into MATLAB by using a package called code generation. And basically we use the syntax MATLAB, variable name, result name, and output name. So we can give these variable names and we can get a MATLAB code which we can run in MATLAB. You can also convert the output of Maple to LaTeX, Python, and C. LaTeX is for typesetting, so it will look nicer. So we can obtain what exactly the equation of motion looks like in the slides. The whole worksheet can also be exported to different formats like PDF, Word, HTML, LaTeX, and so on. If you want more material on how to use Maple, you can please go to this site, and then there is a very nice way of instruction tutorial on Maple. So in summary, Maple can be used to obtain error-free mathematical expressions. So I can find out the elements of the mass matrix, the elements of the Coriolis term, the elements of the gravity term, the elements of the constraint matrix, the derivative of the constraint matrix, and so on. Then we can form the equations of motion and solve the equations of motion in MATLAB or some other software which allows you to use numerical numbers or numerical tools like ODE solvers and so on, which can solve these differential equations of motion. So what I have showed you is one of the computer algebra system which is well known, Maple. It is used reasonably extensively. There are other computer algebra systems which are also available. There is another very well known CAS system which is called Mathematica. It is available from this company called Wolfram. And this, if you are interested in Mathematica, please go to this website, wolfram.com/Mathematica. MATLAB also gives you its own computer algebra system. Okay, this is slightly less well known and less powerful than either Maple or Mathematica, but nevertheless you can use the computer algebra system from MATLAB. For simple examples like the planar 2R or the angular velocity vector or even the 4-bar mechanism, we can obtain everything from the computer algebra system given by MATLAB. So in this NPTEL course, you have access to MATLAB and all its toolboxes. So it's a good idea if you have time to try out the computer algebra system from MATLAB. More details about the computer algebra system from MATLAB is available in this website.